Okay, I'm going to give an update on our Airborne Geophysics project that myself and Kisa Mokanyamale, she's sitting right over here, our colleague at the GeoSurvey. We've been trying to get this thing moving along for years and years and probably a decade, and finally got it going with our project with the Mahomet Aquifer in Champaign County. So I gave an update on this project at last year's meeting. So I'll still go through some of the background of the project and then give you a little bit better update on where we are on the project. Of course, we got to thank a lot of people. Projects like this can't happen without a huge collaborative team, including legislators, local legislators, even up to the federal level. Consortium like yourselves, a group of people that are advocates. We've had direct support from Mayor Marlin, Mayor Finan, everybody. We've had all kinds of help from anyone from the surveys, PRI, the USGS, even down to the Prairie Ogden School District. Were great at letting us drill a hole on their property. So it really does come down to that kind of a collaboration to where people are like, sure, yeah, we'll help you out. So it's been fantastic. We've had a great collection of students from U of I and ISU too, who have been field students for us and manning our field crews. So again, yes, the Mahomet Aquifer. Our goal was trying to figure out a new way to look into the aquifer and study it. So we know that through the decades, for 80 years, we've been studying this thing. Geologists and water scientists started to study it in the 40s and map out where it was, what it was like. Building that information through the 60s, and in the 90s, water survey scientists started doing some actual numerical modeling, really setting up the stratigraphic framework. What is this aquifer system? What are the standards we want to go by with defining it? And then the water survey really started to do some predictive modeling. And then, of course, George in the 2000s really came in and ramped that up to predictive modeling, and George and his team from the water survey. And then so we got back into this and really trying to understand it some more, and Andy Stump and colleagues at the GeoSurvey wanted to better define and refine the stratigraphic framework some more, and we got into the point where what's the next thing to do? Well, technology then developed of doing airborne geophysics. We hired Kisa to kind of lead that program as the technology was starting to explode about 10 years ago. So then we were able to find some funding to do it. The whole point of doing airborne geophysics is to do things faster and better. It's a way to collect data super fast and at a super high resolution, something we've really never seen before and really haven't had that much data density before. So that's kind of things that we're working on as well, is how to handle all the data. The main goal is to develop, again, user-friendly products of understanding where the aquifer is, what it's like beyond what we know right now, and then integrate those data and work with the water survey to integrate all those models and data, geologic data, into their flow models, however they can do it. So we're working directly with them as well. How does the airborne stuff work? It's a helicopter-based system. The helicopter hauls this huge loop underneath it, and that loop has an electrical energy that it emits into the ground. That electrical energy comes back to sensors, basically, and creates a profile of electrical properties of the subsurface, down to about 1,000 feet. And we, from that, then can interpret what the geology is based on those electrical properties. So different geologic materials have different electrical properties. So then we interpret that. Again, back in 2022, Champaign County was the first county in the East Central Illinois to really say, okay, let's do this. So they funded a project that we flew Champaign County. A year later, we were able to secure federal funds through Senator Durbin's office, and again through the support of our collaborators like this group, to get federal funding to fly parts of 4 other counties. to finish off the aquifer all the way to the Indiana state line. And I'll give you a quick little update on where we are with that. But for the rest of the talk, we're basically going to focus on Champaign County specifically. That's where we're diving deep right now into our data processing. What will the data show? Well, what we see in Champaign County is a glaciated terrain. So we see ridges and streams that are all a function of glacial history. So we have these upland ridges that are the glacial moraines up near Gifford. They go across through Mahomet and through the Champaign-Urbana area. We will see those in the data sets. And then the materials that make up those, we'll see the Sangamon River. We see other things that are at sand and gravel deposits versus clay deposits at land surface. We'll also be able to see the bedrock valley that hosts the Mahomet Aquifer. And the geology associated with it. Right now, we have different models of aquifer boundaries and where it is. These are two different interpretations based on two different historical projects. Georgia's boundaries over the years, and Andy Stump mapped the Mahomet in a different way back in the 20-teens. So we wanted to redefine these. We want to test these hypotheses and redefine them. So using Airborne Geophysics, let's map it. So we mapped and flew Champaign County at 650-meter intervals across the whole county. That's pretty tight resolution. We tried to optimize the budget with the flight lines. And there are certainly areas where we couldn't fly. Rural is great, but we can't fly over cities because of FAA regulations of safety and also electrical disturbance anyway. Wouldn't matter because there's too much electricity going on. So overall in Champaign County, we flew 3,079 kilometers of profiles. So trying to map, again, bedrock valleys and then all the material above it, map the Mahomet Aquifer. So a first shot at looking at the data here. This is a perspective view from the south where these are all those profiles at 650-meter intervals. The hot colors, the reds and the yellows, are what we interpret to be generally coarse grain, potentially aquifer-type materials. The cold colors, the blues and the greens, are going to be clay-rich, more electrically conductive. It's not one or the other, but we have to then use our geologic brains to interpret the rest of it. But overall, we can see generally through the central part of the county where we expect it, there is the Mahomet Aquifer. There are other things that we try to interpret. First thing is the boundary. Where is it? Of course, we want to know where it is. These are the boundaries interpreted by George and Andy over the years. And that's the southern boundary of where they've interpreted it based on boreholes, for example, and other mapping throughout the year. But as we just take a first shot at looking at this, we can kind of resolve, hey, well, maybe this boundary is a little bit more complicated, a little different than what we can resolve out of boreholes. So it's a good thing that we're starting to change that kind of perception of how to map this thing and where it is. What I didn't show last year was this, where we can take a different look at this thing to where we can start looking at horizontal slices through the data vertically. And that really helps us understand where things are changing vertically in the geology. So as an example here on the left is a profile of the data. Again, a bunch of different colors, blues being fine grain stuff, reds are, we think, more coarser grain stuff. And there's a data gap in RAND tool there, and just a profile of what the resistivity values mean. And then we can kind of interpret the resistivity signal, put in some geologic contacts, and then try to interpret the geology from that. And this particular profile is a generalized profile up there in the northern half of the county. So we're going to, again, and that particular horizontal slice is right around an elevation of 560 feet. So we're going to go through the geology here, starting at the bottom. at an elevation of about 360 feet. This is a slice through the HTEM data that is below the Mahomet, below everything, and it's in the old bedrock. So this pattern we see of the blue and the red, that's all in bedrock below the Mahomet Aquifer. So these are old limestone and shale deposits. So this red blob is a limestone dome, basically, in the rock. And then all around that dome is filled in with shale, very clay-rich shale. So the electrical signal is different between the two, but we know it's rock and not Mahomet. So then from here, we're going to go up through the sequence of elevation slices. And we start to immediately see at an elevation of 400 in the lowest part of the Mahomet Aquifer down there south of the town of Mahomet, we start to see it come in. And as we move up through the sequence, we start to see how it fills in, and it actually bifurcates. There's a northern part and a southern part that goes northeast and northeast of the town of Mahomet. We've kind of known that's been there, but now we can really start to map where it is and how thick it is and what it's like. And that bifurcation kind of goes away as we get to the top of the Mahomet, and the signal becomes hotter near the top of the Mahomet. And so we're trying to interpret what does that mean? We know that there's some indication that there's cementation at the top of the Mahomet sometimes. Is that an indication of the cementation, or is it coarser grained? We're still getting into trying to interpret that. As we get up above that Mahomet, we start to get into more clay-rich materials. We still see the signal of the Mahomet there that's probably combined with some shallower sands, but we also see, if you see north and south of the main channel, we start to see these little tributary channels of what we interpret as sand coming into the main Mahomet. These are things that we've known were there. We've never been able to map them before because it's hard to find boreholes that map something that complicated. So this is really cool to start to see these tributary channels in the shallower sediments. And then we get up into the more greens and the blues where we're all up into the clay that's capping off the Mahomet. And these, again, are slices of like 30-foot slices of average values. So we can refine this even more with even thinner slices and get more refinement of the signal. One little case study we were happy to see is back in the 90s, the town of Homer, which is east of Champaign-Urbana, Homer needed some water, so they hired us to go out and do a ground-based electrical survey to try to find them some water. So they did all this ground-based stuff, same as the Airborne, but just all ground-based. It took them weeks to get all the data, it took them months to process the data, and they came up with this report over the course of about a year in 1996. What happened? Well, they did find some water. Up there, there's a little Hatcher pattern, and the town of Homer was able to put 2 wells in there, and those wells give them about 1 million gallons a year, I believe. About enough for a small town like Homer. So then, in 2022, we went in and flew it with the HTEM, modeled those data, and now we see exactly where that little channel goes and what it connects to. So all those little green patches and more where it's the yellowest, we can interpret that as being these little sand lenses that are about 100 feet down below land surface. And that's where Homer is drawing those wells, where their water is wells are getting the water at those 2 points. So what I've mentioned before is that little sand lens that goes all the way up to those wells is right along Windsor Road. So as you leave Champaign-Urbana, you're driving down Windsor Road. Now you know that about 100 feet down, you're driving along an old ancient river valley that's about 100 feet down. So pretty sweet. We were very excited to see something like this. And then the old geologist that did that whole study was like, oh my gosh, it took him a year to do it, and we flew the whole county in 7 days. It was crazy. So this whole process is changing our perception, really, of how to map the aquifer and what it really looks like in a third dimension. So, this is kind of our old perception of it. Now we're starting to understand the third dimension of it and how different entities of the aquifer are fingering out in a third dimension. So it's really fun to start to change our perception. From a cost effectiveness standpoint, just a little back of the envelope kind of cost assessment. This whole project for about 2.5 years is going to cost us about $1.5 million total, with our time and what investments from Champaign County have contributed. If we were to do the same thing without Airborne, just on the ground with a full-time student staff who never get a day off for 12 years, it would cost us about $7 to $10 million and take us about 12 years. And we'll never find students who would do that at $15 an hour. So here's some of the technology we do use on the ground, the TEM technology. This is Kisa and our staff out there. And we use this for calibrating the airborne data. And we use a lot of this. Right now we're in the phase of actually doing some 3D geologic modeling. We haven't come up with even our preliminary models yet, but I wanted to show you some of the examples of how we're doing it. We are using a custom software called Geoscene 3D, which was built for this particular data set. Like Geoscene 3D is used for HTEM data generally, a lot. So it's just this kind of software interface where we can view data in a profile view and map view and 3D view, and this is how we're then using our geologic brains to interpret all this. Gives us all kinds of tools for making interpretations and drawing boundaries and stuff like that. And so it's really exciting to just bring in all those data. We have a full-time staff hired that helps us use this, coordinate the data and use the software. And there's a team of about 4 of us who are doing this. And eventually, we want to build something like has been built before in other projects of online 3D model viewer and data manager where a user can go in and slice and dice a geologic model, export data, view different types of data, all in an online setting. And we have this available for other models that we'll eventually try to migrate the Mahomet over to. I wanted to skip forward and show some of the stuff we are doing with that software, or the way we're trying to interpret the data a little bit. I didn't want to get too much into the weeds in this, but for example, this is an interpreted cross-section that Andy Stump did back in 2016. So he used borehole data, and he's done a fantastic job of setting up interpreted cross-sections of the general geology of the aquifer system. And then we try to overlay our signal on that and try to see, how to calibrate our signal. And we have different ways to display the signal. We call these, like, you see the word sharp inversion. There's smooth inversions. There's blocky inversions. And we're exploring all different ways to try to show it. So we can see how different geology is matching with the signal itself and where it doesn't match. So this is one of those ways we can use different color ramps to isolate different things. This is the last one I'll show of this is how we can, a lot of it is visual, where we have the signal and then we isolate different intervals of the signal to show us where the sand lenses are, potentially, where the clay stuff is versus where the mixed stuff is. And then the signal can show us variability within the sand. So if we can interpret it properly, we can see within the Mahomet potentially where it's gravelly or over here, or where it's sandy over here, where the water chemistry may be different than over here. So it's a huge, huge effort of that kind of stuff right now. That's kind of where we're in the depths of it right now. So yeah, our final objectives are kind of moving into migrating this whole thing into a water survey effort of improving their predictive models. Our HTEM airborne timeline, the Champaign project was supposed to be done in 60 days. So we asked for an extension. I think we'll get that extension. We're not going to be done in 60 days. So we'll probably be done more towards the end of next year, and which will likely include that the Ford Iroquois area as well. We've flown that. Kisa's in the middle of processing all those data, and we'll start interpreting those data next spring as well. and kind of combine it all in with the Champagne data. So we're excited. We have a team of 4. We're trying to build that team even larger if we can. And hopefully we'll get there. We'll get there. So I'm happy to take any questions if you'd like at all. Yeah.